Okay, let's look at a couple more examples. The first one is not first one. This is actually the second example I gave. This is example 6.5. Okay, the previous example is a 1D conservation momentum problem, right? This one is a 3D problems. Okay, I will show you how do you solve 3D problems in the three components x, y, and z. You need to calculate the force components separately. Okay, so the problem is this. Okay, this is a bend. Okay, it's a bend. It's a pipe bend. Okay, the fluid is oil with a specific gravity 0.94. So you should be able to calculate the gamma, right? 30-degree bend. Its angle is 30 degree. The diameter of the bend is 1 meter. Okay, pretty big. Inlet and outlet, section 1 and 2, right? The flow rate is 2 cubic meter per second. So, you know, conservation mass, flow rate in and out the same. So both inlet and outlet have the same flow rate. So you should be able to calculate the velocity, right? The weight of the bend without the oil, the empty weight is 4,000 Newton. Okay, empty weight. The volume of the bend is 1.2 cubic meter. Okay, so you should be able to calculate the weight of the oil. Okay, the total weight should be able to calculate. Okay, pressures P1 and P2 inlet and outlet have the same pressure, 75,000 Pascal gauge. Okay, so these are all the known values. The question is to ask you to calculate the force required to hold this bend in place. Okay, similar to the last example. Last example is a 1D, right? The force required to hold the 1D pipe structure, right? Last problem. This one is also the force required to hold this bend in place. Okay, so you're asked to calculate the force. So it's obviously, it's a conservation of momentum problem. That's your first choice. If you see a problem like this, ask you to calculate force in the test, and it should be a conservation momentum, should be your first try. So again, the same questions you ask. Is this problem steady state? Is this uniform flow? Because if you have these two conditions, your equation is a little bit simpler, right? So it is a steady state. It doesn't change with time, sure. Okay, so you don't have the momentum change in terms of time. So you have one less term in the equation. It is a uniform velocity inlet and outlet. Okay, it didn't say, but it just gives you a flow rate. So you can assume it's uniform flow. Okay, if it's non-uniform, usually it will tell you it's non-uniform. Okay, so that should be a little bit easy. So the equation should be simple. It's just summation of force equal to the change of momentum. Okay, and you don't need the integration. Okay, so the same process will solve problem as the previous example. You draw the two diagrams, free body diagram and the momentum diagrams, and then after you correctly draw the diagrams, again write down the equations. Okay, let's look at each diagram separately, see if you know how to draw these diagrams. Okay, so first of all, you detach this object from the support, which is supported by the phalanges, right? So if you detach the support, you draw a free body diagram, you have to detach the object. You have to replace by the force. Okay, you don't know what the direction of the force at the beginning, right? So you just assume Fx, Fy, and Fz, three force components. Okay, that's the force required to hold it. You know, in your equation, you will have three unknowns, Fx, Fy, and Fz. Okay, these are the force required to hold it. For the direction, you don't care at this moment. You don't know the direction. Then you just always specify the positive direction, same as the dimensions, axis, x-axis, y-axis, and z-axis. Okay, so you assume it's just positive force. If the result is negative, that means the direction is opposite, right? Okay. What are the other forces? You have a weight, okay? It's the total weight. It's not only the empty band, the weight of the empty band. It should be the total weight, W. Going downward, X, Y, Z. Z is, a positive Z is going out of the paper. So the weight should be negative Z direction, going downward. Then you have a pressure forces, P1A1 and P2A2, okay? In this problem, outlet, you have 30 degrees. So in the real calculation, your outlet force, pressure force should be, you should also separate them into the X and Y components for the calculation. Okay, these are all the forces. Okay, then momentum diagram. It's a little bit easier. Momentum diagram, you have inlet momentum, mass flow rate, inlet times velocity inlet. Outlet, you have a flow momentum going out. Again, momentum is also a vector, right? So you also need to separate them into the X and Y components for the momentum at the outlet during the calculation. Okay, so if you can successfully draw the free body diagram, then you can write down the equation easy. X, Y, and Z. You have 3 equations to write, okay, separately. So X component, summation of force on X direction will be equals to the momentum out at the X direction minus the momentum in at the X direction, okay. Summation of force based on the free body diagram. P1A1 is positive, Fx is positive from your assumption. Then P2A2 cosine 30 degree is a negative pressure force, right? Let's look at the direction. So it's negative. So equals to momentum out and minus momentum in at the X direction. So momentum out is mass flow rate 2, velocity 2, times cosine 30 degree, that's the X direction momentum out, minus momentum in is m dot 1 v1, okay? This is the X direction. Same thing for the Y direction. The force component will be P2A2 sine 30 degree. Now it's going upward, so it's a positive, right? Fy is positive. And the momentum out, look at this, momentum out is going downward, okay? m dot 2 v2 times sine 30 degree, but it's downward, so it's negative, okay? Minus the momentum in the Y direction is 0, so that's the Y equation. Z equation is easy, simple. There's no momentum in Z direction, right? The flow is only in XY direction, so the right hand side of the equation is 0. The left-hand side is just the summation of the force. Basically, your force required to hold it in Z direction is just to overcome the total weight. That was the weight of the empty band plus the weight of oil, okay? So these are the 3 equations. If you write down these 3 equations, you're halfway through, more than halfway through. Next is just the calculation. So after you write down the equations, you do some, check it a little bit. See, look at, examine the equations, right? So your Fx, Fy, and Fz are the 3 unknowns. All of them are in the 3 equations, so it's good. You have good directions. So your goal next is just to find out the rest of the letters in the equations, okay? Find out the values, okay? So I put this in this corner, okay? These are the rest of the values, okay? So velocities, you have V1 and V2 in these 3 equations, right? V1, V2. V1 should be the same as V2 as we said before. Uniform, the conservation mass, flow rate the same. So in and out, you have the same velocity, which is the flow rate divided by the cross-sectional area. So 2.55 meter per second is the velocity, both V1 and the V2, okay? Mass flow rate, you need the mass flow rate, same thing. Mass flow rate m dot 2 should be equal to m dot 1, conservation of mass, same mass flow rate. Mass flow rate is just density times the volumetric flow rate. All of them are given. Density of oil, 0.94 specific gravity, times the density of water, 1000 kilogram per cubic meter. 2 cubic meter per second is the volumetric flow rate. So it is 1880 kilogram per second. So I guess you have everything, right? Pressure is given, so should be able to calculate. Okay, so Fx equal to negative 8,530 Newton, Fy is negative 31,800 Newton, and Fz is 15,100 Newton. Okay, the weight of oil is really simple. It's gamma oil times the volume. Volume is given. Gamma oil is 0.94 times the gamma of water. Okay, 9,800. So you should be able to calculate that easily. So these are the three forces. So notice Fx is negative. That means the force is in the negative x direction. Fy is also negative, is negative y direction. While Fz is positive because the weight is going downward. It's negative weight. Weight is a negative direction, right? In z direction. So Fz will be positive. So if you write down into the vector form, this is the final solution. So I, J, and the K. These are the Fx, Fy, and the Fz. Okay? So this is problem 6.5. A 3D steady state uniform flow conservation of momentum problem.